In this video, we'll talk about vectors as an introduction to them. So, first, let's talk about what a vector is. If we consider the physics definition, a vector is anything that has both magnitude and a direction. Okay, so what that means is basically, consider yourself if you're driving in a car. You're driving, say, 50 miles an hour. What matters also is which direction you're going. There's a huge difference going 50 miles to the east as opposed to 50 miles to the west. So if we have a vector, typically it's going to have a size. That's your magnitude. And it's also going to have some sort of a direction. Typically we think of it as an angle. That would be our direction. Kind of like using the compass, like a cardinal direction. You're X amount of degrees from north, from south, from west, from whatever. That's typically how we think about it. Okay, so let's talk about what a vector would look like in mathematics. Let's pretend that this blue arrow is a vector. That's typically how they draw them. Now, unlike in typical geometry, this arrow here doesn't indicate that it keeps going. It ends right here. That is your end point. Now, if a vector is in standard position, it always starts at 0, 0. Let's say we're on a coordinate grid. So you have your x-axis, you have your y-axis. Okay. Now, there's a few ways that we determine this in mathematics. One way is to determine your length, or your magnitude of your vector. Let's call that L for the moment. And let's call the angle between the x-axis and our blue vector, let's call it theta. Now, if I'm looking at a vector, I could give it in the forms of you go L distance at the angle theta. That's typically how we would think about it. In standard rotation, counterclockwise is positive, and then clockwise being negative. So you could have a vector with a negative angle. It just means it's going downward. Like positive 270 degrees would be the same as negative 90 degrees, for instance. And then L is just a distance away, however far away from the origin. Now, as an alternate way to write vectors is what they call component form. Basically, I'm just looking for the coordinate here. This point right here has an x-coordinate and a y-coordinate. If I were to put it on the coordinate grid, it would. That's just kind of how these things would work. So the idea is I would look out how far over and how far up. Now that makes a right triangle. This can come into benefit, it can come into play if you know the component form you can solve for the other forms. So typically when we write a vector, we'll use these pointing brackets and we'll just have the length going across and the length going up or down, and we'll have the pointy brackets there. Or, like we mentioned before, you can say you go L distance at a theta angle. Okay, we've talked a lot about the theory. Let's put this into practice a little bit. So right now we have a vector in component form. That's what these weird brackets mean. And I want to put it in standard form. So basically what I need to find is I need to find L and I need to find theta. Those are the two things I need to find. Let's draw a picture first. So if I'm on a coordinate grid, I went to the right 3. That's what x is, right? So let's say I went over 3. And then my y, I went up 4. So meaning my vector looks something like this. Now the cool thing is this makes a right triangle. By definition, x and y are perpendicular to one another. So I know I have a 3, 4, 5 triangle. That makes it pretty easy to find L. I can apply Pythagorean theorem, so we can check it if you like. So I have 3 squared plus 4 squared, and this has to equal L squared. If I run this down, then I get 9 plus 16 has to equal L squared, therefore L squared has to equal 25, and L has to equal 5. So there's L, halfway there. Now, I want to find this angle right here. Since this is a right triangle, I can use right triangle trig. I feel like that would be the easiest way to go about it. Since we were given these two lengths, let's go ahead and use those two lengths. This would be our opposite side here and our adjacent side here. So if I think about which trigonometric ratio uses opposite and adjacent, that would be tangent. So tangent of theta has to equal opposite over adjacent. So 4 over 3, which means that theta has to equal inverse tangent of 4/3. Which if I run in my calculator, I will get that theta has to equal 53.13 degrees, roughly. So in standard form, my vector is 5 units at 53.13 degrees. Okay, let's look at another example. This case, we're given a vector in standard form, and we want to find the components of it. Okay, so this is a little bit different than what we've done before. We're not on the coordinate grid. We're using the compass. They're giving us a direction as it pertains to north, west, south, and east. So, first off, let's go ahead and draw our little compass here. Let's say that's north, east, south, west. Looks something like that. What this is saying, if I go 10 degrees north of west, meaning that if I start at west, I go up towards the north 10 degrees. So I know I have a vector that looks something like this. And I know this size is 50 on the hypotenuse, and I know this angle is 10. Now, knowing what we know about vectors, we can make a right triangle here. It's going to look something like this. Now, all I'm looking for is this distance x going across and the height of my triangle, y. So if I bring this over here just a little bit, I have a right triangle that looks something like this. Got a 10-degree angle there, hypotenuse of 50. I'm looking for x and I'm looking for y. So this is a right triangle. I can use right triangle trigonometry. I know the hypotenuse. I know an angle. So let's go ahead and get started. So if I know the hypotenuse and I know y, which in this case would be opposite of the 10, I know that sine of 10 degrees has to equal opposite over hypotenuse, y over 50, which means that sine, or rather 50 times the sine of 10 degrees has to equal y. I can apply the same logic with the x. Knowing what I know about it, I can say, instead of sine, using cosine, since x is the adjacent side. So cosine of 10 degrees is equal to x over 50, which means that x has to equal 50 times the cosine of 10. So if I go ahead and punch these both into my calculator, I get y is roughly 8.68, and x is roughly 49.24. Now here's where I have to consider the component form. Consider the picture again. If I turn back to the picture, my y is positive, that's fine, it's going up. My x is going to the left, which would make it negative. So if I was to write this in component form, I'd need my weird bracket. The x is negative, so this would be negative 49.24. The distance is still, it's going 49.24. The negative just indicates it's going to the left, not to the right. And then, since the y is going up, we just keep that one as is. It's positive 8.68. And then I have something in standard, or in component form, not standard form.